Hey everyone, welcome to this Zoogla Fireside Chat featuring two awesome quantum computing entrepreneurs. I had a chance to meet both of them in person earlier this year, and I wanted the Zoogla community to meet them and hear from them. Through that, I invited Shirayu to actually conduct this Fireside Chat as he knows 100x more about quantum computing than I do. So I'm so glad that Shirayu agreed to do this moderation, this Fireside Chat. We got to know each other quite a few years ago now when we first started the Zoogla community. Shirayu has been at Google for quite a while, over two stints. He started in the San Francisco office in BD from 2011 to 2016. And then he actually moved over to Singapore, where he was an investor at the seed stage fund called Seed Plus. And after a few years there, including actually being invited to the Prime Minister's office, where he's a technical advisor for the National Research Foundation there, he went back to Google, and that's where he's at now. He's been there since 2019 in a business development role. But thank you, Shirayu, for giving up your time to conduct this awesome fireside chat for the Zoogla community. I'll turn it over to you to introduce our entrepreneurs and conduct the fireside chat.
Thanks, Chris. Hello, everyone. Hi, Joe. Hi, Yan. And thank you for making the time. I really appreciate it. You know, as an entrepreneur, I'm sure like this, your time is like super premium. So I really appreciate it. And thank you from the rest of the community. So to get us started, maybe, what we can do is just, hear a little more about each of you. And I'd love to hear the story, right? Like, how did you all get started with this idea? Like, there's always sort of this, you land up with the idea from various angles, and you build a company. So I'm always curious, like how entrepreneurs land up there, and then the element of like really hard to build technology that exists. So just love to hear, I guess the narrative that goes behind the difficult part of building your company. So, anyone can go first. So Joe or Yan, decide who wants to go first, and I'd love to hear a little more.
Jan, do you want to take this one first?
Well, I can. Thanks. And yeah, thanks also to the organizers for giving us the opportunity to speak here and tell actually our story. So my name is Jan Goetz. I'm one of the founders of IQM, which is a company headquartered in Finland, in Helsinki, building quantum computers. So it's very much a hardware focused company. And we are building computers based on the superconducting technology. So for those of you who have heard already something about quantum computing, there are still different base technologies out there which you can use to actually realize such a system. And we are using the superconducting technology, which is, for example, also what the Google team is doing, or IBM, many of the big ones, but quite a few startups as well. So as many startup founders, actually, I have a scientific background. So I was working in academia for quite some time, doing my PhD, my postdocs. And then at some point, I was doing a postdoc in Finland at Aalto University. This was the time when in the US, there were already quite a few startup activities out there. This was 2018 or so. In Europe, not so much. And when my postdoc time was over, I was sitting down with my professor, Mikko Möttinen, and we were thinking, okay, what to do? What's the best way, actually, if you really want to build a large-scale quantum computer? And we realized that probably it's not going to happen in the universities. Universities are usually good in developing individual components, maybe trying to push the limit of certain effects or so. But when it's about large-scale engineering of complex systems, this is rather done in industry usually. It's more engineering task than science at some point. So we decided that it's better actually to do it on the private sector. And since there are no Googles or IBMs or so in Europe where you could just join an established company. This was the reason why we had to create our own company, our own startup. And this is what we decided to do end of 2018. We then were lucky enough to get our first investment round together beginning of 2019. This is when we started the operations. And meanwhile, actually, we are operating here from our headquarters in Finland, but then we also have an office in Munich, in Germany. We have around 40 to 50 people there. We have around 150 people here in Finland. And then we have two smaller offices, one in Paris and one in Spain and Madrid, where we have 1 or 2 people each. Where we currently are from a, let's say, product or commercialization point of view is that we have first prototype systems that work. So we are currently working on a 20-qubit system, and our business model is to actually sell the complete system. So it's a bit different than what you see also from many US-based startups, which are more focusing on the cloud business. We are very much focusing on getting the systems out there in the field, and the early adopters are scientific computing centers, because they are already interested in the technology now. With 20 qubits, you cannot do something that provides commercial value, but you can do nice scientific experiments, you can education and other important tasks. So this is what we do. We have sold 2 systems. One is already delivered. The other one in Munich is going to be delivered soon. And I think there will be more to follow up in the future. So this is roughly where I come from and what our company IQM is doing.
Yeah, Joe.
Okay. So yeah, I can tell you a little bit about what we've been doing. My name is Joe Fitzsimons. I'm the founder of a company called Horizon Quantum Computing. What we're focused on at Horizon Quantum Computing is essentially trying to take, 70, 75 years of classical computer science and condense it into about 7 years for quantum computing. At the moment, if you look at the state of programming tools for quantum computers, they're really, they're sub-assembly level. You're piecing together your programs gate by gate by gate. And that's, not a great state of affairs, particularly because the hardware is very diverse. As Jan mentioned, there's a lot of imperfections in the hardware, and you need to make, a significant effort towards error mitigation. But even on top of this, quantum computing just works in a fundamentally different way to conventional computing. It's all about exploiting these kind of physical effects, this kind of quantum interference between different branches of a superposition, different branches of a computation, and trying to use both constructive and destructive interference to get some kind of benefit in exploring the space of possible branches. So, the way I look at it is, if we had quantum computers tomorrow, if we had large-scale quantum computers, the equivalent to my MacBook Pro, but if we had that with a quantum chip with trillions of qubits and they're all noise-free, we still wouldn't really be able to take advantage of it. We know a few things we could do with it. For sure, it will be useful for certain things. But our ability to make use of it the way we can make use of conventional computing power today is really extremely hampered by the fact that we have limited set of techniques. The programming tools we have are really, really primitive. And the reality is most of the domain experts in areas where quantum computing is likely to play a major role do not have the expertise to be able to take advantage of a quantum computer for whatever task they're tackling. So, I had, like Jan, I come from an academic background. I had been a professor before. Actually, I was a National Research Foundation fellow here in Singapore. I had built up a fairly large research group, got tenure, but the whole time I was thinking that I was not likely to stay in academia long term. I got into quantum computing because I figured it was the field that would give me the highest probability of being able to kind of relive the excitement of the computer revolution or the PC revolution or something like this. And when I was picking subjects for my undergrad, when I was, deciding what to do for a PhD, I basically was trying to figure out what's the best way to be involved in advanced technology. And I got it into my head that I better get a PhD, otherwise people wouldn't let me do it. This was massively misguided. Don't do that if you're listening. But it's what I thought at the time. So I went down this path in quantum computing. For me, it's always been about trying to get to a real technology that people use. And, I would say through the 2010s, it became increasingly clear that that first of all, it was becoming more possible to build quantum processors, that there was more space for the hardware companies to come into existence and to start actually making progress. I'd say from about 2015 onwards. And then the other side of this is also, there's kind of a shift from where you can make progress. The center of gravity starts shifting away from academia and towards industry. So for me, it was always going to be this path. 2018 seemed about the right time. We figured it would be, maybe another 18 months until someone built a quantum processor that couldn't easily be simulated. It turned out we were wrong, and it was 21 months. And it was the quantum group in Google that were first to demonstrate this. We figured we should be in before then, because if we wait until after that point, there'll be a surge of interest. There'll be a million startups. Everyone will be trying to get into the field. So now's the time to jump. And there's dangers to jumping too early. There's dangers to jumping too late. So myself and a couple of my group members decided to take the plunge, raised a seed round, end of 2018, quit our jobs, moved into the startup full time from March 2019, raised a few more rounds since then. At this point, we've been building up tools to essentially automatically accelerate conventional code so that you can write a program in MATLAB or in C, and automatically construct the quantum program for it and compile it all the way down to something that can run on hardware. It's a pretty long path. We've most of the key parts of this demonstrated so far. We're generally the only ones that can do this kind of algorithm synthesis. And we're able to do things like compile C and so on down to subroutines that can run on quantum computers. And we've started doing that. So we're still pre-launch, but we've shown a lot of the technological milestones along the way.
That's awesome. I picked up on a couple of things, right? I think both of you spoke about the shift of center of gravity away from academia towards industry. So, and seems like 2018-ish was the time frame. Just wanted to sort of dive deeper into that, and Jan as well. I mean, this question's for you. What really fundamentally changed, and what that you saw that initially it was academia? Were there sort of some trigger points that led to you thinking that now it's kind of moving more towards industry, and there are use cases that are coming up that seem more real than being science? So just wanted to know like what's changed, and I wanted to kind of dive deeper into the way the system works, right? For example, Joe, you spoke about building for basically taking code that people write on MATLAB and then basically converting that in some sense onto into code that quantum machines are able to understand. And this is something that I wanted to kind of touch upon slightly later, because I want to understand what goes into what are the architectural choices that companies are making, and would yours, for example, work across different kinds of quantum computers based on the base technology, or would it sort of be dependent on to only specific hardware? So I'd touch upon that a little later. I'd love to understand first, like the science versus industry shift, and since both of you spoke about it.
Yeah, so maybe if I start again, as we are a hardware company building the complete systems, this is something that in the end is a very complex undertaking. And what you see is there are actually quite a few academic efforts which aim for the same thing. There are big consortia, many groups are working together on this. And this is usually not very efficient because everyone is working on a different part of the computer, let's say. And what we thought is that it's just much more efficient if we had one team which all together working on building the complete system, so that the know-how is within the team. And also, of course, in the end, you need quite a lot of capital if you are developing such kind of hardware. So now, especially for the superconducting approach, the way it works, these processors, they are being produced on silicon wafers. So we are working on 8-inch silicon wafers, and we do the complete design. So you need some kind of, in semiconductor industry, it's called EDA tools, electrical design automation tools, but those don't really exist, for example, for quantum processors, because they follow slightly different physics and so on. So for example, these tools need to be developed, and then you need to have the fabrication up and running. So a whole process line for superconducting technology, and then you need all the test systems up and running. So all of this is very complex and very capital intensive, and usually you don't get amount people and also money into an academic framework, at least not if you want to do it in a single place. And this is why I think many people have realized that actually building a large-scale system, it can be done much more efficient if you do it in a company. And of course, also it was then heavily benefiting from the fact that more and more corporates will kind of invest into quantum. They don't invest huge sums. Usually, if you look at them, they have maybe smaller teams and they're trying to figure out what are the applications, but at least it was a lot in the news. And of course, this helps then again on the investment side. So then also we were living in the world where capital was still relatively cheap because there was a lot. Maybe now this is changing, but this I think also stimulated that quite a few startups have been formed. And in this sense, I think there was both the pull from the industry side, but for us, actually, as a hardware company, this didn't matter so much. Of course, it's important that some applications are out there, but especially when we got started, it was more of getting actually our fabrication up and running. We didn't talk a lot about applications. Maybe now we are getting to this point because on a 20-qubit chip, you can already try out something and test some algorithms. So now we are getting more into this application side, but especially in the very beginning, it was mainly the goal to really create a critical mass of talent, because in the end, at the moment, also we see a huge shortage on the talent side, and then also create enough, let's say, financing power to build a company that in the end can compete on a global level. So this was mainly for us from a hardware perspective, the motivation to do it then back in 2018.
Yeah, I can also give a little bit more explanation for why, why the timing seems to make sense. For me, the time. So I have this slide that I show whenever I'm giving public talks about kind of what the timing has been like. I got into quantum computing in 2004. At the time, the largest system I think was 7 qubits. There had been 3 qubits demonstrated, I think, in '97, something like that, and it had kind of progressed slowly. So the way I show it, I show different segments of the growth in number of qubits over time, with various cartoons of me being, enthusiastic, depressed, and now super happy. But basically, what happened for a long time is that there was a concentration on getting the basic operations, the basic qubits, better and better and better, because the initial versions that were seen in the late 90s, early 2000s, the quality of the interaction between qubits, the polarization of the qubits, so your ability to initialize it in a particular state, the quality even of single qubit gates of readout, were all low. So you could maybe do a demonstration, and then it might be a big deal if you can demonstrate entanglement, which is, kind of quantum correlation. And so, you started to see these improve slowly, but in order to get to a device that you can't easily simulate, you need at least about 40 good qubits. And if you're talking about simulation on a large cluster or something, then maybe more like 50 very good qubits. And so for a long time, we did not have very good qubits. We had very bad qubits. And those qubits became better over time. And I have a very, a very strong memory of going to the American Physical Society March meeting in 2012, when a team from IBM showed benchmarks for their system that looked like they were getting the errors low enough to start to be able to correct them as they went along during a computation. So this is something we call fault tolerance. And we're not really at the stage of seeing fault tolerance actually implemented yet. But this was the first glimpse that it actually maybe the operations had gotten almost to the level of being able to do this. And I think what's happened in the field since then is that, okay, the quality of the best qubits available has continued to increase, but maybe not at this, but alongside that, people have started to build larger devices. And up to that point, that wasn't really the case so much. So if you look at a plot of the number of qubits in a device, and qubits are basically bits, they're just quantum bits. So you can think of this as bits of memory in a device. For a long time, there wasn't even a byte of memory in a device. Now we're at the point where we have, you know, maybe even 20 bytes worth of memory in our devices, but that's how early we are in this. It's really like the equivalent of the 1940s. However, the devices, if you plot the number of qubits, the doubling time has gone from once every 5 years from the period from, you know, late 90s to, you know, mid 2010s. Well, mid to late 2010s, and late 2010s, it has significantly increased, and it's more like doubling on the scale of less than a year now. So the rate at which devices are growing in complexity, it's much, much faster than Moore's law in this period of time, when before it was much, much slower than Moore's law. So there's really this kink in the log plot. So there's really been a shift in what's happening with the technology. So I think that's really what's going on. That's driving interest in the field. If we went back to, you know, doubling qubits every 5 years, then people are going to say it's going to take just way too long to get there, to get to the scale of systems we need. But at the moment, things are moving pretty quickly. So I think that's, you know, that's a large part of why now is the right time.
That's awesome. Thank you. The second part of my question was more around, and I think this is directed to you, Joe. You spoke about, you know, what you're trying to build, and it feels like, you know, you're letting people, you know, you're meeting developers where they are today. So you can write a program in MATLAB, and your company basically is creating the tools that convert that into a form that quantum computers can understand. So the question, I guess, was, when you kind of think about building these tools, how much of it is what specific to certain kind of quantum computers? How much of it's specific to sort of base technology? I know Jan spoke about like the superconducting, you know, approach to building quantum computers, and I know there are like a few others in the market, including Xanadu's taken a certain one in Canada, and that's different from some of the others. So I'm just curious to know, like, when you speak about building your tools, are they sort of dependent on what lies underneath, what kind of computers are being used?
The way we approach this is in kind of building up abstraction layers. So the highest level, we're doing the algorithm synthesis and so on. So we're abstracting away the quantum mechanics entirely. But layers below that, we have a hardware mapper layer that maps to the connectivity of a given processor, to the instruction set of a given processor, does all the logic synthesis to go between different gate sets and so on. So that it's relatively straightforward to address the majority of types of quantum architecture that are available. Things do not run equally well on every hardware. If you set up qubits in a line, so each qubit is only connected to its neighbor along a line, it's definitely going to take you n steps for qubit 1 to talk to qubit n, or n-1 steps. Like, there's just no way around that. Whereas if they're in a 2D architecture, if it's kind of a regular lattice in a plane or something like that, that's going to shrink down to square rooting. So there's for sure different kinds of connectivity within the device will result in different overheads, kind of between linear down. There's quite a lot you can do at compile time to try to mitigate this. Instead of keeping your information physically located in particular places, you try to shift it around all the time, so it's always going to be near what it needs to talk to. And once you get down to about once you get up to about 2 dimensions, it starts to work pretty well. 1D is still pretty bad, but anything from 2D up is pretty good. So from that point of view, yeah, we can handle most architectures that are around. The synthesizing a quantum algorithm from a classical algorithm, that's done at a level of abstraction that does not really care about the hardware. Yep. The process you go through, though, what we do, we try to break apart loops, we try to break apart recursive function calls, break down to simpler and simpler elements, then recognize elements and replace them with more efficient ways of doing the same thing. And that, you know, that works at a pretty high level of abstraction, but it also results in kind of hybrid algorithms where some parts get quantum accelerations and others don't. And in principle, you can take into account information about the size of the system you have available to see whether you should bother doing it for a particular acceleration. Should I bother with it? Should I not? And that, yeah, you can take into account hardware information. However, there are other kinds of devices out there that are not fully fledged quantum computers. So you mentioned Xanadu. So Xanadu do something called Gaussian boson sampling. And there's companies like D-Wave that build devices called annealers. And these are both kind of sub-quantum models. So they're systems that are not full quantum computers yet. For Xanadu, there's a pretty clear path to getting to a full universal quantum computer. But for D-Wave, I mean, they've been talking about it for a long time, but they're doing what they're doing, and it's not a quantum computer. So that we will never try to target. It just works in a completely different way. It's a different kind of thing. You know, it's like trying to say we target quantum computers, but also ASICs or something like that. It's just a different thing. So that's kind of where we are. We target any gate model quantum computer. In principle, we can do stuff outside the gate model as well. In practice, though, we don't. But pretty much anything. We're not restricted to qubits. We're not restricted to any particular instruction set. We can target pretty much any hardware you can dream up. And it's all done in a way that doesn't require us to hard code anything. We just take a processor description. But there's still some systems that we can't target because they're not universal quantum computers.
Understood. I think there are questions from the audience. So why don't we turn over to some of the questions that are being asked. So I think Ashok's got a question. And the question is, how does the quantum algo derive from a classical one compare with the original? And are there any performance comparisons, and what would you use to sort of measure them? I guess will also be useful to know.
Sure. So I mean, there's a couple of different ways. There's quite a number of different metrics you might care about. Probably the most practical is actually wall clock time or something like this. But you might also, care about the amount of memory utilization or something like this. From our perspective, the way we do this, the transformations on the program that we do, they're designed to never make it worse, so that it will never slow down the program by more than a factor of 2. So the quantum program will never really be slower than the classical program, and oftentimes it will be accelerated. However, you can come up with classical algorithms that you cannot accelerate. An example of this is computing parity. If you have a long string and you want to compute the parity of the bits in that string, if you take pairwise parities and you take parities of the result of those the whole way up, so you have a kind of binary tree that comes in, it's basically impossible to beat that. No quantum computer can help you beat that. That's about as fast as that task can be done, with or without quantum processing. So I can't say quantum programs will always be faster, or there's no way for me to say that our compiler will always accelerate code. Sometimes it won't. Sometimes things are just as fast as they can possibly be. However, what I would also say is that the speedups can be dramatic. So for things, generally for for loops, while loops, and things like this, if they are, if things don't change many passes through, for example, so, if you've got a condition right inside the loop or something like that, and everything is wrapped up in that if statement or something like this, then we can skip through a lot of the cases and avoid it evaluating that code, avoid it evaluating the increment entirely, so that we skip forward. We kind of fast forward through the parts where nothing's happening. And in those cases, you get a quadratic speed up. There's also things like when there's a lot of linear algebra used where you can get exponential speed ups. So there's a lot of different kinds of structures that can show up in your program that get different kinds of accelerations. And those can be, I mean, it's rarer that it will be constant. Oftentimes it's removing stuff at compile time and pre-computing it. It's, you know, using quantum algorithms that have a quadratic or better speed up, or in some cases exponential speed ups. So it can be really significantly faster, but not in every possible case.
Maybe one thing to add here also from my side, at least this is the view that we have in our company, is anyways that the quantum computer, or the term quantum computer, is maybe already a little bit misleading, because it won't be like a standalone machine where you only have the quantum part. Anyways, you always need to have a classical machine that controls the quantum computer. And I think in many cases that are now being discussed, it's also about these so-called hybrid algorithms, where you have some part being executed on a classical machine, and then the more complex parts of the algorithms are being then outsourced to the quantum processor. So it's an interplay between the classical machine and the quantum machine, similar to, for example, you do this also in AI or so with the graphical processing units, where you use them as an accelerator. So I think this concept of an accelerator is probably more suitable to describe a quantum computer, rather than saying it's a quantum computer that you have and you have then an operating system on it and all this kind of stuff.
So I fundamentally disagree with Jan on that. And I mean, I will put my hand up and say that I'm in the minority of this view, but my view is that quantum computers are computers, and that we should treat them like computers. At the moment, they are not very capable computers at all. But long term, they become very capable devices that are capable of everything a conventional computer is capable of. And it has become quite, you know, common knowledge to view quantum computers as some kind of accelerator, as some kind of appliance for solving optimization problems. And I think that's selling them short. Now, I fully understand where Jan's coming from this. I don't fault him at all. I don't even really disagree with him. I'm just saying that the way I view quantum computers is fundamentally at odds with this way of thinking about them.
Just to kind of move things along to a different direction, I think you know, one of the things that comes up often is commercial applications, right? And what are the target commercial applications? At the end of the day, since both of you are building companies, I'm sure that the thought process is around solving specific problems, whether it is for research or defense or whatever that is. I just wanted to hear, you know, from both of you, where do you see the biggest scope for this, and you know, how do you see that playing out in your specific companies? What are the target areas that you all think will first get commercialized from a quantum computing standpoint?
Well, I think I mean, what already is happening now is that people do some kind of science with these machines, because what they're obviously very good at is simulating quantum physics. And if you look at the number of papers that are being published from algorithms that are run on all the different machines which are out there, I think this is quite impressive. So if you can, I don't know if you can call it a use case or not, but I think the first use case, as in many other tech areas as well, is science. So do fundamental research with them. And then, at least this is my view, is that they will transition out from this more and more into applications. And of course, then it's hard to say when do they really start creating commercial benefits to the company. So let's say if you're a company doing chemistry and you want to simulate complex physical systems or so, often you also in these companies, they do very fundamental physics. And it's hard for them to tell whether these simulations actually will end up in a product maybe a few years down the road, right? So it's really hard to say, I think, at which point in time is it now really commercial value that they add, or is it still on the R&D side? But at least my opinion is that we will see this transition from fundamentals, basic science, where we are right now, maybe into more and more applied research, which still then benefits the R&D teams of probably big corporates, maybe in chemistry or other fields. And then I think from there it will become more and more, let's say, a system that will help us also in everyday applications that we have.
I think it's super hard to argue with chemistry as the first application. So it's just too close to what quantum computers naturally do. There's too strong a parallel to what they do to quantum chemistry for it not to be a really good fit. Beyond that, of course, we know of certain applications. We know there's applications in well, we know there's application to cryptanalysis, but that's a pretty niche use case. But you see a lot of applications, there's a BCG report that looks at the value creation for quantum computing at different timescales, but basically it identifies 4 different use cases. It sees one as cryptography, by which I take it to mean cryptanalysis for the most part. Another is optimization. A third is simulation, meaning chemistry simulation, material simulation, condensed matter physics, that kind of thing. And then the fourth is AI/ML. And for machine learning, that's actually not a near-term use case. So people play at the moment with these classifiers. So there's this area of quantum algorithms called variational quantum algorithms. And the basic idea is that you do not know how to solve the problem. So you guess a quantum circuit for the problem, and then you tweak the parameters of that circuit using something like gradient descent or stochastic gradient descent to train it as you would train a neural network. And actually, sometimes people call this kind of approach quantum neural networks for the same, reason, because of the high analogy to neural networks. The problem is, that's not how you would program a computer for most tasks. Right? That's not how you would want your laptop to be programmed for most things. For certain tasks, of course, that's that allows you to do certain things in pattern recognition and whatnot that you couldn't otherwise do. But can you imagine trying to make every piece of software by training a neural network to do it? That seems like you lose a lot of structure. So when I think about, what the different applications are when we talk to different, different organizations, different industries. A lot of it for me, the machine learning stuff, that's further off because we need something for the algorithms that really do give you a speed up, give you a provable speed up over classical algorithms and an exponential speed up at that. You need something called quantum random access memory. Which is a kind of coherent memory that you can query in quantum superposition, and we do not have that at present. None of the devices that are being implemented in industry are capable of doing this. And that kind of puts big data applications on the back burner. You can think of that as being in backlog. For the moment, what we have, what we're starting to have is small devices with very limited memory. But they're capable, they're going beyond what can easily be simulated. So the first things we're likely to see solutions to are problems that have small descriptions, but take a long time to compute. That have small input, small output, but the computation in between is difficult. A lot of this can be things like differential equations, linear algebra, matrix algebra, tensor calculations, things like this. That's pretty ubiquitous. You see it in things like you see large inverse problems in oil and gas. You see it in aerospace, simulating turbulent fluid flow. Like we still have wind tunnels because we can't simulate turbulent fluid flow well. You see it in things like simulating masks for photolithography. You see it in lots of different areas where there are these hard computations that need to be done that are ultimately, matrix calculations or systems of differential equations being solved, something like this, where actually quantum computing, there are good building blocks for this. We would expect to see large speedups. We maybe lack the tools, lack the expertise to really make killer applications in that place. And for sure, the hardware is not there yet to really be able to do these yet. But I think there may be what's next. The first application we'll see with real industry impact, it's almost certainly chemistry. It's just so close to what the hardware does. There's a lot of work on black box optimization, and I have less faith that that will do well compared to optimization for chemistry, because ultimately that's what nature does. Like, it does it the way a quantum computer will do it.
Got it. I think just going back on the two different views of what quantum computers are. One is sort of it's a computer by itself, standalone, and the second is it's an accelerator, and it's in combination with a classical machine. And you mentioned that you are in a minority, so I just wanted to understand, like, since you mentioned in the minority, kind of, can you double click on that? Can you like expand why is that the case, and what's your point of view on why you think that's not how the worldview is generally?
Sure. So I mean, Jan is right that the way any quantum computer works, and he would know this more than me since he actually builds them, is that you have a lot of classical control that is driving your quantum chip, that's driving the quantum phenomenon, that's stacking up your pulses going into it, that's processing what's coming out of it. Actually, even like if we want to get to a point, a lot of what's run on these devices, we call them quantum circuits at the moment. It's basically it's equivalent to basically a classical circuit. You just have a list of operations, they get run, and then there's some readout at the end. If we want to get to a point where we can do general computation, we actually need to have something a little bit different, something more like a GoTo program or something like that, where you have fragments of circuits, lists of instructions that are run through, and then there's a branch. And at the branch, you measure something, or conditioned on some measurement, you decide what state the control hardware should go into next, and that will determine the next list of instructions. But for the most part, that's not the way the control hardware works at the moment. But you can, even if you get to that stage, it really is a symbiosis of the two, of some quantum processing going on with some classical processing deciding how to do it. That's necessarily true, and I have no argument with that being true at all. So in some sense, anything you do will be some combination of classical processing and quantum processing. However, what generally happens is this is extended, particularly in the domain of these variational algorithms, to say that you need to do a lot of classical processing in close proximity to the quantum processing. And this isn't just for the control systems, but rather what you're doing is, you're deciding what program to run next. You run one program entirely, you get some measurements out of it. Now you decide from those measurements, how am I going to pick the next circuit to run? And that's what these variational things are doing. It's the parameter tuning I mentioned earlier. They're essentially training the circuit, whether it's a classifier, whether it's supposed to be an optimal solution to something, whether it's supposed to be a ground state for a molecule. But you have this classical processing going on in close proximity. But I do not have much faith in these algorithms. So these variational techniques. I think they'll be great for chemistry. I don't think they're going to be great for optimization and other tasks. This gets into an area where there's just not very many theoretical results showing that they will do well. And there's barriers to why they won't. So there's this notion of barren plateaus. You get into regions where it's very hard to optimize. You're searching around in basically a flat space for a gradient. So you're not really seeing any gradient. You don't know which way to move. So that this is really a barrier. There's lots of work to try to circumvent it. There's lots of work on different kinds of approaches to variational techniques to try to get around this. But overall, I think they'll work really well for chemistry because it's mimicking what nature does. But I don't think they're going to work for black box optimization all that well. Whereas a lot of the community, particularly on the industry side, has put a lot of faith in the variational algorithms. particularly because you can start to run them on today's hardware. You can start to do experiments today. It's very convenient for them to work, but I don't think they do. I mean, that's basically it. And we won't know. We won't know until we have larger systems. It's just, you know, it's a bet on the future.
Maybe one thing here also, at least where I see a clear use case of this model, is the error correction itself. At least for me, it's quite obvious that you need some classical computing power to take part then of the error correction. And this is not then the variational algorithm. It's a different kind of use case. It's maybe not so much the accelerator picture then anymore, but it's more like a, I don't know how you would call it, interplay between the two systems.
Sure. And I mean, if you're thinking of like minimum distance decoding and all of this kind of thing, like for sure, it's the case that it's really hard to decode some of the error correction codes that we look at for fault tolerance at the moment. And, you know, the minimum weight perfect matching and all of this kind of thing is like it's a hard computational problem. It takes a long time to solve, given the readout. So you can think, well, I need a supercomputer to error correct my conventional computer. Sorry, to error correct my quantum computer. But I don't know that, I can't see the latency being good enough on that for it to ever actually make sense. But like, at least the way I see it, we're going to have to do less good decoding and get the physical error rates down low enough to enable fast decoding, where the decoder's not as good, but it's much faster. So I can't see how we can get away with anything more than like constant time decoders, or maybe like log or log decoders or something like that. But it needs to be super fast. And I don't think supercomputing is going to be the answer for that. But you know, that's not to say my answer is right on this. It's just, yeah, who knows what way it will go. This is just my guess at the direction it's going.
We have one last question. I think we're fairly sort of close to time, so I wanted to make sure that, you know, we have we can get this in. So Ashok asked this question again. Can you kind of talk us through the revenue models that you have in mind? How do you kind of make money as a company, right? Like what are you selling and to whom and who pays? So, you know, Jan, if you want to go
I can start, because I think anyways, it depends also a little bit what kind of a quantum computing company you are. As said, we build systems and our business model is to sell the complete systems. This is actually also partly why we have such a strong view on this hybrid model, because the customers for the actual systems, these are computing centers, supercomputing centers, and they're very much used to kind of doing this kind of computing. So here, with the story that we are telling about these hybrid accelerator quantum computers, this is also, in a sense, a business argument, because we need to create this product market fit. And the market here are the big computing center. And why are we doing this? Well, there are several reasons. But for us, actually, it's on the one hand, it's financially very lucrative to sell out the systems, because people see a lot of strategic value in just getting the technology on site and being able to host such computers, because it might be that the technology becomes very powerful at some point. So there's a huge strategic value. This is why there are a few numbers out there of systems being sold. There are more than 10 million or 20 million US dollars or so. So quite substantial amount of money that is being paid for getting such a system. And then on the other hand, the quantum computing as a service, so the cloud-like model, of course, it is valid if you have something real to compute in the cloud where you get the benefit back. And this is something that we don't see yet. And for this reason, for us as a startup, it's actually quite a lot of investment to put systems into a cloud where we have to maintain them all the time and make sure that the quality stays up and at a stable level. And this is much easier for us to do with clients we know, where we work together, like these scientific computing centers. And this is why we just think it's not yet the right time, maybe, for the cloud computing, at least not for a company like us. Maybe in the future, if there are good applications, and Joe can talk about this, the kind of software as a service model becomes much more attractive. But right now, we are focusing very much on really the hardware sales cases.
Yeah, so yeah, I mean, for us, we make software development tools. So there is the economics are different. We're not giving people a physical system. At the same time, a lot of the stuff we have to do in the compile on the way down is computationally expensive. So we do actually use quite a bit of computational power to compile. But for us, it's pretty straightforward. The intention is to offer our tools in a SaaS model with usage-based pricing. So, the more value you get out of the deployed program, the more revenue will accrue. Now, how would something like that work is a good question, but it turns out that at least for the next few years, there's a very strange notion in quantum computing, and maybe people don't think about it often enough. But essentially, when you compile for a particular system, your code essentially gets stale. So your best compile for that system, 4 hours later, a day later, a week later, a month later, that will no longer be the best program. It will no longer be the best set of instructions to do that particular thing. The systems are recalibrated from most of the hardware manufacturers at pretty regular intervals. Of course, it varies from manufacturer to manufacturer. The actual performance of the systems varies over time. I mean, they're sensitive, like quantum computers are essentially extremely good sensors. So they're pretty sensitive to stuff happening in their environment, various different changes. So how the system is operating at any particular point in time, the compilation you need to do to maximize performance, it changes. So this means if you want your program to stay up to date, you don't want to compile it once and then save it. Rather, you want to be continuously recompiling it with the latest characterization, so that when you go to run it, when you go to call that program, you're using a compilation that has the latest characterization, that has the latest crosstalk mapping, maximizes the cancellation you can get, all of this, and that means people using our tools not just to write a program once, but also to keep it fresh. And that's not something that exists in conventional computing, right? Because conventional computers are really reliable, but quantum computers are not really reliable yet. I would love us to get to a point where this business model no longer makes sense, where the code doesn't get stale and it does exactly what it's supposed to do, but we're years from that.
Awesome. It's a lot to think about. And don't have any more questions. So I think we're coming up on, I can give you a few more minutes back, but Chris,
Great.
do you have any questions? Or...
Sure. Thank you, Shiraya, for conducting such an awesome fireside chat. Maybe the thing I'll ask is for both Jan and Joe, thanks for giving us so much of your time to educate the Zoogla community here. What ask do you have of the community, whether it's looking for hires that you want to hire in all your different locations? This will go out to the global community, or even partners or customers. How do you think Zoogla Schools will potentially work with you?
Sure. So, I mean, for us at least, we're right in the middle of an expansion at the moment. I realize it's maybe a less certain time in technology more broadly, but for us, actually, we're in a pretty good position. We have way too much runway at the moment. We've 10 years runway at the moment, so we definitely need to shorten that. So we're hiring at the moment, and we're looking for software engineers. We're looking for people on product. We're looking across the range of different functions. So for sure, if you're interested in working with quantum computers, if you're interested in running software on some of the most, I'm not going to say the most advanced computers, given that I've just said that they've only a handful of bytes of memory, but if you're interested in working really at the cutting edge in terms of software, in terms of software development tools and things like that, please reach out. I'd be delighted to hear from you.
Great. In terms of locations, you want these people to be based at, Joe?
So, I mean, we're open. We're pretty flexible at the moment. We're based in Singapore, but we're open to people remote. We'll be opening an overseas office soon, but we've yet to announce the location on that.
Great. So anywhere outside Singapore, could be Europe, could be America as well. So
it'll be Europe.
Jan.
Yeah, basically the very same thing here as well. So always looking for great people to join. I mentioned earlier already, there is a shortage of talent, and I think not only for quantum, but the whole spectrum of people that we need. Also, we have just recently closed the funding round, so we are expanding. At the moment, as mentioned, we are mainly focused on Europe, but there might be also new openings coming up, either maybe even in the Singapore area or somewhere over there, or then also in the US. But then, of course, also, let's say on the user side. So if there's anyone who thinks that there might be interesting projects that could be tried out on a system, or anyways, maybe related to supercomputing or so, we would be very happy to get in touch as well.
Awesome. So to clarify, Singapore for you, Jan, as well as Europe, and then maybe America, and then for you, Joe. But Singapore, clearly you're based there. Europe for sure. And for any Americans, a lot of Americans actually are on this list.
Yeah.
Would you sponsor them to either go to Singapore or go to Europe as well?
Yeah.
Perfect.
Or to work remotely, whatever. Drop me an email.
Great. Ashok, I think you came on. Maybe you have a final question for our guests.
I just wanted to thank both of them. You know, it was a very learning experience for me. I'm a nuclear engineer by education, but on the fission side, not on the quantum side of so much. It's more on the nuclear power side. But it was a very interesting. I started learning about quantum algorithms, and you know, when I was in Google, there was some articles used to get published a lot. I was very interested in them. So yeah, thank you so much. It was rewarding to listen to both of you, Joe and Jan.
Thank you, Ashok. I'm sure they'll both love to speak to you afterwards, so I'll make sure to pass on the email. So thanks, Ashok. And again, thank you, Jan and Joe, for spending so much time with us and educating us, and good luck with your businesses. And Shari, thank you again for moderating this fireside chat to make it such a great learning experience.
Thank you.
Thank you.
Can I say one last thing before we go, which is just that even though I disagreed with you on a couple of things, I have tremendous respect for what they're doing. You know, it's a really hard thing. So it's also another great company to look at if you're looking for places to go. Sorry, I just needed to say that before we.
No, it's always great to have panelists not agreeing 100%. So I think you provided a good panel discussion. So thank you to both of you.
I think.
Thank you.
If the panelists agree on everything, I think it's not a good discussion, in my opinion.
Yes. So thank you, Joe, for doing it for us. Enjoy the rest of your day.
Bye.
See you guys.